So far in this section, I've covered several examples of how using immutable objects can leave you open to unintended side effects. In this video, I'll show you one way to minimize these, the immutable object. An immutable object doesn't change state once it's created. An immutable object is a secure object, meaning that calling code can't maliciously or mistakenly alter it. An immutable object simplifies concurrency design, which we'll cover later. This slide describes the strategies of creating a class that, when used, produces immutable objects. Make instance fields private and final. Do not define any setter methods. Create defensive copies in any getters. Use a constructor or factory method to set data, making copies of mutable reference data. Mark the class final or make all constructors private. In this video, I'll walk through the first 4 of these strategies in code. I'll discuss final classes and private constructors in upcoming videos. I've created a new project called Immutable Classes with the main class. Let's imagine that we're creating a genealogy program and we're tracking people, names, birth dates, and kids. I will start out with a person class. I'll add some fields using basic encapsulation techniques. For this exercise, I'm just going to have name, date of birth, DOB, and I'll just make that a string. And also have a field, kids, and array of my person class. I'll generate both getters and setters for all the fields. I'll also generate a toString method, but select none for the fields. I'll add some code to print out the person data. First, I want to deal with printing out the kids information. If there are no kids, I'll print NA for not applicable. If there are kids, I'll set up a name string array, because I only want to print a list of the kids' names. I'll return name, date of birth, and kids string. Next, I'll add the code to populate the names array and build kids string. I'll use the setAll method on the array's helper class to populate my names array. The parameter for the lambda is an integer, an index. I'll first use that to get the child from the kids array. That could be null, so I'll use a ternary to check for that and set the name to an empty string, otherwise I'll set it to the kid's name. I'll use the join method on string, joining all the kids' names by a comma. Okay, so this is a typical class, pretty well encapsulated. The only way to access the data is with getters and setters. I didn't even set up a constructor. I'll create a couple of persons for my genealogy database in the main method. Since I didn't declare any constructors, the only one I can use is the default no args constructor. Jane will be one of the kids. I will just set her name for now. And I'll do the same for Jim and Joe. These will be the 3 kids of John. Finally, John will be the father. I'll set John's data by using the setter's first name and then date of birth. I'll use the setKids method to pass an array of persons with an array initializer, passing Jane, Jim, and Joe. Finally, I want to print John's data. This is a perfectly reasonable way to create a class, though it's somewhat tedious to create a new person. If I run this, I see that I have John, date of birth is May 5th, 1900, and his kids were Jane, Jim, and Joe. The object John is definitely not immutable. I can use the setters to change any data on the object. I'll change John's name to Jacob, for example. I'll also use the setKids method, passing it 2 new instances of persons constructed with no data, and I'll print John out. Running this to check the results. You can see that John is no longer named John, and his kids are now nameless, and there's only 2 of them. Again, depending on what the case for your genealogy application is, this may be a valid way to design your class. Let's at least create 2 constructors to make the job of creating persons a little easier. Back on the person class, I'll generate the first with all 3 fields. The second constructor will just have name and date of birth, DOB. I want to remove those statements. Instead, I'll chain a call to the other constructor and pass null as the kid's argument. Now let's say I really don't want the code to change name or date of birth after the person object is constructed. To protect against this, I'll remove the setters for those 2 fields. First, I'll remove the setName method. Then I'll remove the setDOB method. getting back to the main method in main, my code no longer compiles. I'm going to comment all this code out. I'll now create my persons using the new constructors. For the first instance, I'll pass Jane, and I'll include a birth date, January 1st, 1930. For Jim, maybe he's 2 years younger than Jane, so February 2nd, 1932. Next Joe, and let's use March 3rd, 1934. To set up John, I want to create an array of persons for his kids. I'll set up an array variable, John's kids, using an initializer with Jane, Jim and Joe. I'll create John with the constructor that takes 3 arguments, John for name, birthday 5th May in 1900, and John's kids. I'll print John out. If I run that code, I get the same as before. The code is a little more succinct and easier to read. I can't change name or date of birth, but I can still set the kids. Let me try that. I'll set the kids to a new in-place array initialised to a new person, Anne, born 4th April 1930. And I'll print John again. Running this, you can see John's kids have been completely changed. Let's adjust the kids a bit more. First, I'll set up a local variable and assign it the result of calling getKidsOnPerson. I'll set this first kid to my Jim instance and print John's information. If I run this now, John's kid has changed from Anne to Jim. This could be a problem. You might not expect your client to change the kid's data outside of Persons Operations doing it. What if I assign my local variable kids to null? Does that have any effect on John's kids? Running this code has no effect on Jim's kids, so that's a good thing. This means reassigning the reference or setting it to null from the client or calling code doesn't change kids. I'll call setKids and pass the kids variable, which we know is null, and print John again. Running this code, you can see I've managed to remove all John's kids. I can only do it by calling the method on person, so that's at least some control going back to the person class. This is a very common kind of class, where some parts of the class is mutable. Next, I'll create a person record in comparison. A record solves a lot of the problems for designing an immutable object, but not all. My record, person record, will have the same 3 fields as the person class, name, DOB, and kids. But for the kids, the type will be person record. We want a constructor for just name and date of birth. I'll generate a constructor using the standard IntelliJ tools, but watch what happens when I generate a constructor in a record. We get these 3 options: compact constructor, canonical constructor, and custom. We're going to ignore the first 2 options and select custom here, which will lead us to the standard dialog you normally see. Later in this section, I'll discuss those other 2 options that popped up. Instead of passing a 0-element array, I'll change 0 to 20. This means I have a placeholder for 20 possible kids. Now, I'm going to copy the toString method I had on person and paste it here on this record. Okay, so that's all I need to do right now. I'll create a new class called mainRecord and add a main method. I want to copy the code in the main class, main method, lines 23 to 30, and paste it in mainRecord. I want to replace all references to person with person record. Running this code now, I get the same output I got originally when using the person class. I'll create another John variable, JohnCopy, and assign that a new person record with the same name and date of birth as the first John, but no kids. Running this. You can see it looks a little weird because I'm printing 19 commas and no kids' names because of the way I have it coded. I initialized kids to be an array of 20 person records, and each array element is initialized to a null reference. I can't set the kids on this record, but I can change them, which is why I set this up this way. Let me do that. I'll create a new local variable, a person record array called kids, and assign that John copies kids. I'll set the first element to Jim, and the second to a new person record, Anne. I'll print John copy. And now running this code, you can see I can set and change the kids in the kids array on my record, meaning these instances are mutable. For this reason, you can't assume just because you're using a record or setting up a record that the record is immutable. If the fields were all immutable types, yes, but if you're using arrays or collections or mutable types, then you can't use a record and prevent side effects without implementing some defensive measures. A record satisfies several of the requirements for an immutable class design. It uses private final instance fields, it has a constructor to set the data, and it doesn't have any setters. What's missing is it's not creating defensive copies. Let's add this to the person record. I'll add a getter, picking the kids field. I'll replace return kids with a statement that first checks if the kids are null. If so, it returns null. Otherwise, it will return a copy of the array. I'll use arrays.copyOf. That takes an array, and the length of the array I want to copy. If I rerun my code in the main record class, you can see whatever I'm doing in the client code, it's not changing the value of the kids array on John copy. Now, you may feel like you've created a type that's immutable, but don't congratulate yourself just yet. Consider this minor change, where I'll change my local variable John's kids, element 0 to a new person, say Anne, born April 4th, 1936. This code happens long after I created John with his kids. If I run this code, you can see I'm able to change John's data, his kids array, by changing the array variable I used to construct the record. This means I need a constructor that will create a copy of the array passed before I assign it. I won't do this here for this record, but I wanted you to see there are several reasons why a record might not be truly immutable. Of course, there are many cases where you want to support some mutability, but this should be by design, not by accident. If your class must be mutable, you should still use some of these techniques to minimize mutability. In the next video, I'll walk through creating my own immutable person class. See you in the next video.